In this lecture, we will learn about thermal spray coatings. We have learned how necessary are the coatings to impart certain functionality, because the overall performance of the material is decided by the overall bulk properties of a particular material. So, the device or the implant will work based on what the bulk material is composed of, whereas its interaction with the surrounding environment is very well dictated by the surface. So, we need to impart certain properties such as corrosion resistance, wear resistance, even cytocompatibility. So, that is being basically provided by certain coatings. So, in this lecture we will learn about thermal spray coatings. How do they impart a surface layer for a bulk material to impart certain functionality. Thermal spray, it is an effective means of depositing materials either in molten or semi molten state for achieving thickness which are approximately greater than 50 micrometer thick. Essentially more than 90% of the coatings for biomaterials is basically being utilized by thermal spraying. So, thermal spraying is a very versatile technique in terms of depositing a coating onto an implant surface or a biomaterial or an implant or a device material. In the thermal spraying, the molten particles are accelerated. So, once they accelerate, then they are impacted onto a substrate. So, they are being heated while they are in flight. So, the molten particles, they are accelerated, they impact on a substrate, and upon impact with the substrate they undergo rapid solidification, which basically results the deposition or the buildup of the coating. So, the main thing about this particular process is that substrate is maintained at the lower temperature. So, in turn we are not heating the bulk material. So, the properties of bulk materials, they are not altered in any case. So, the bulk material property are what basically remains what we really targeted at, or the overall fabrication of the material of the bulk material remains as it is. So, there is no degradation of the property of the bulk material, and also there is no deformation of the substrate. So, that is the plus point of the thermal spraying. The deposition is occurring not because of metallurgical bonding, but because of the mechanical interlocking. So, deposition is occurring by mechanical interlocking of the species or of the molten particles which impact the substrate and get deposited. Some sort of diffusion bonding or metallurgical bonding occurs if the temperature is maintained a little higher. So, in process the diffusion is allowed to a certain extent, and then it creates also a secondary bond which is much more stronger, that is called diffusion bonding or metallurgical bonding. Other adhesive, chemical and physical bonding mechanisms can also occur, such as oxide films, formation of van der Waals forces, etc. So, we can see thermal spraying, it utilizes depositing a material which is generally greater than 50 micrometer in thickness. It accelerates the molten particles, let its impact on a substrate, and it undergoes rapid solidification to form a final deposition, and this deposition is mainly by mechanical interlocking, and eventually because of enhanced thermal energy which is being imparted, it can also impart some sort of a diffusion or metallurgical bonding, and also van der Waals forces or oxide film formation can also occur during thermal spraying. So, thermal spray process is a versatile coating technique, because more than 90% of the depositions, they are done by thermal spraying. The beauty of thermal spraying is it can impart metallic coating, ceramic coating, cermet coating, or even composite coating. So, that is the versatility of a thermal spray process, that it can deposit either metallic, ceramic, cermet, or a composite coating. It is utilized for corrosion protection by providing a certain ceramic layer, wear resistance to impart wear resistance to a particular material. It can also provide thermal insulation such as thermal barrier coating. It can also provide oxidation protection by providing high temperature oxidation resistance. It can also be utilized for reclamation. Reclamation is nothing but repair of a certain damaged surface. So, if I need to if a particular part is now being damaged, it will be better if we can reclimate it instead of making the new part again. So, we save the money, the cost, as well as time. So, if I see a damage on this particular material, I can reclaim it. I can do the reclamation part by thermal spray process, because it is one of the very rapid deposition technique. So, it can deposit a material to a very high extent, couple of kgs in an hour. So, we can repair this particular material very quickly. So, that is nothing but reclamation. At the same time, we can also provide near net shapes of high temperature alloys, ceramics, intermetallics and composite materials, which in turn reduces the overall wastage or the scrap which is produced during a processing of a material. Because in any case we cast a material or we build a particular material, then we need to basically scrape out the excess of material to get to the near net shape. But in thermal spray process we can make a negative replica and then we can deposit the material to get a near net shape. So that minimizes the wastage which is basically incurred during the processing of fabrication of a material or a coating. So we can see thermal spray process, it can deposit metallics, ceramics, cement or composite coatings, very well utilized for corrosion, wear, thermal or even high temperature oxidation. It's very well utilized for reclamation because of its high deposition rate, and it can also produce near net shapes of high temperature alloys, ceramics, intermetallics or even composite materials. The advantage of thermal spray processes include that the thermal energy can be controlled very easily. In case we can decide what is the kind of energy which is to be applied. So for melting aluminum I might require very low energy, whereas for melting aluminum oxide I might require very high energy. So I can control the energy input in terms of melting aluminum or aluminum oxide. So the thermal energy can be controlled in thermal spray process. Again, the plasma gas and particle velocity, such as in plasma spraying or even in a high velocity oxyfuel spraying, we can achieve subsonic to supersonic velocities. So depending on the kind of deformation we want, if we want thermal energy to play important role or we want to play the impact energy to play a vital role. So by plastic deformation or by just the melting and resolidification, we can control what sort of deformation process we require to deposit a coating. Also we can impart much more compositional flexibility. We can play with the powders or wires which are to be deposited, and then we can control what is the feed rate of those powder particles or the compositional wires to achieve a gradient coating. So in that terms we can define the overall compositional flexibility of the coating which is being developed. And in case of electric arc, we can provide this reverse transfer arc, which can also provide removal of oxide layers which inherently forms on very reactive materials. So if we can somehow provide reverse transferred arc, we can avoid the deposition of oxide layers. So in turn we can generate much more smoother interface or much more integrated interface with the coating material. Again, in this process thermal spray basically is inherently has very high or rapid solidification. So in turn we get very refined microstructure, and refined microstructure, it means that we can achieve very drastically improved properties, mechanical, corrosion, any wear resistance. So such properties we can achieve via achieving a very refined microstructure. So in turn what we can get multi-layered structure, we can get a graded structure. Also we can control the porosity or the composition. So that is the advantage of the thermal spray processes. So we can, in case when we require a graded porosity, so that the cells can really extend their arms and anchor to the coating material. So that is very essential in terms of bio coatings. So they need some interaction with the cell surrounding cells. So cell can extend their arms in the porous, and then they can enhance the overall integrity with the device or the implant material. So we can see thermal spray processes, it has a controllable energy term, that thermal energy can be controlled. We can achieve very high velocities. It can provide compositional flexibility. It can remove oxides if required to get an inherent or integrated adherent coating. We can get refined microstructure, that in turn improves the overall properties, and we can get either multi layers, graded and controlled porosity, or even varying compositions. And there are certain factors which define the bonding of this particular coating with the substrate. So first thing is we are going to synthesize the coating by terms of mechanical bonding. So the first bond which is forming is via mechanical bonding or mechanical interlocking. So first thing is we need to make the substrate very rough in order to adhere the coating or let the coating get mechanically interlocked with the substrate. So first thing is cleaning and grit blasting. If there is already some dirt present on the surface, that may not allow the coating to get deposited or may not allow it to integrate with the substrate. So we need to clean the coating, and then we need to grit blast it. Grit blasting is utilized for roughening the surface. If I have a very flat surface, then it is very hard for anything to stick onto it. But if I have a very corrugated surface or rough surface, if an entity comes, it can basically get locked at certain locations, and that will provide it much more adherent coating. So, that provides more chemically and physically active surfaces that will result in a very good bonding. At the same time, we are providing much enhanced surface area, and that increases the overall coating bond strength, and also this rough surface provides mechanical interlocking or mechanical keying. So, that is what we can see here, that the rougher the surface, the better will be the overall mechanical interlocking of this particular material with the substrate. The refined microstructure can be attained because the individual particle cooling rates are in the order of around 1 to 100 millions per degree centigrade, million degree centigrade per second. So, we see the cooling rates to the order of 10 to the power 6 to 10 power 8 kelvins per second. So, that is the cooling rate we are talking about. It is 10 to the power 6 to 10 power 8 kelvins per second. It means the cooling rate is very drastic. As soon as a particular material is heated, it will cool down to room temperature within fraction of a second. The cooling rates are to the order of very high, 10 power 6 to 10 power 8 kelvins per second. So, they can attain the room temperature in time period of say less than around couple of milliseconds. So, that is the overall solidification rate we are talking about. The thermal interaction is very important, because that will lead to the eventual diffusion bonding, but that is again dependent on the temperature and time that is imparted to the coating material. So, if we have sufficient heat available with the bottommost layer, because as soon as we are depositing a material on a substrate, we are also inputting certain heat energy to the substrate. So, eventually we see the overall heating of the substrate material to say couple of 100 degrees up to 100 degrees centigrade or in that particular order. So, we can see the thermal interaction is very important as well to decide the overall diffusion bonding which can occur between coating and the substrate material. So, apart from mechanical interlocking, we also have some metallurgical bonding which can generate, or it can also lead to van der Waals force attraction to further make the coating much stronger. So, providing increase in thermal and kinetic energy, we can increase the chances of metallurgical bonding. So, that is dictated by temperature of the molten particle, velocity of the molten particle, even the enthalpy, the mass, density and specific heat content. So, depending on all those parameters, we can achieve a variation in the coating properties. And there are certain types of thermal spray processes which are available for deposition. First is combustion flame spraying. That basically is nothing but combusting of fuel, but in this case we achieve very low flame velocity which are to the order of 50 meters per second, and flame temperature which are lesser than 3000 degrees centigrade. So, the problem with this one is we can't melt ceramics. Ceramics, they have very high melting point. So, melting ceramics becomes much more difficult, because for melting the ceramics we need to make it enough molten as well that they become much more, they can be easily deformed plastically and then they can get deposited. So, that much heat is not available with the combustion flame spraying. So, it provides much lower performance of the coating. Also, the velocity is very low. So, the impact it is not strong enough to fill all the pores which might be present on a rough surface. Second category is high velocity oxy-fuel. It is a special torch design which can achieve very supersonic velocities to the order of Mach 4, which is approximately 1200 meter to up to 2000 meter per second. Though the temperature of this flame is little lower because it is again coming from combustion, but it has very sufficient impact energy available for plastically deforming a material, soft material such as aluminum, copper, nickel, such material. But it is rarely used for ceramics because the plastic deformation is very limited for ceramics. So, ceramics are inherently heated via or coated via plasma spraying or vacuum plasma spraying. In case of 2-wire electric arc spraying, we can get very high material throughput. It means we can deposit a very high quantity of a material. At the same time, since we are saying 2-wire electric arc, it means we need 2 electrodes to generate an arc. So, one electrode material can be nickel, other electrode material can be copper. So, what we can do, we can produce even bimetallic coatings. It can even have more than 2 electrodes. So, we can again impart much more variation in the composition if required. Plasma spraying. Plasma is nothing but ionized gas. So, it can achieve very high temperatures to the exceeding 15,000 Kelvin. In this case, we achieve particle velocity of around 2 to 3 Mach. So, molten metal particles, they can be accelerated to velocities of starting from 200 meters per second to approximately 1000 meters per second. So, they can generate enough velocity, at the same time they are very high temperature. So, in this case we can melt ceramics very easily, they can be plastic enough to get reshaped onto the contours of the surface, and they have very high velocity as well to fill in the pores. So, it can also generate very good coatings, but still they can generate certain porosity, they can also have oxide inclusions, they can also have residual stresses and even unmelted particles, because even oxides can form, and since the velocity is so high, the time may not be sufficient to melt the entire particle. So, we can also achieve some unmelted particles. We have one more process which is called vacuum plasma spray. So, basically it is utilized for oxidation, for avoiding the oxidation of the alloys. So, in certain materials such as nickel, cobalt, chromium, aluminum, yttrium alloy, if we spray them in air, some oxidation is a possibility of this alloy. Even titanium, tantalum and such metals which are prone to oxidation, those are basically preferred to be sprayed in under vacuum condition. So, we utilize plasma spraying under vacuum. So, in this case preheating of substrate that handles oxidation and self annealing of deposit or stress relief can also occur, and in this case we can also build very thick deposits. Again if we enhance the recrystallization, it will result in enhanced particle bonding. So, there are certain advantages of vacuum plasma spraying, that we can avoid oxidation, we can achieve much denser coatings as well, because we are creating plasma which will allow the porosities to be eliminated, and in turn what we are getting very dense coatings of these particular materials. So, in turn we can see thermal spraying, we have either a solid billet or maybe some powder feedstock that is basically being heated up first. So, we heat it, and once it is heated it becomes a molten droplet. Those are now accelerated via certain media, any carrier gas, and then they tend to impact on a very rough surface. So, we have surface which is very rough, mechanically rough, and then these particles they start getting deposited onto the rough surface as what we call splats. So, we had a roughened surface, and then we can see the deposition of this material. In process, the oxidation of these particles, the molten particles can also occur, and that can lead to oxide formation as well. Some particles they can remain unmelted, because the overall heat which is being acquired by these particles depends on the velocity of this particular droplet. So, if you supply very high velocity, there may not be enough time for it to acquire enough heat to get melted, and in turn it will just impact on the substrate without getting melted. So, that is again thermal spraying. We can also get something called arc spraying. We have one electrode positive potential, second electrode negative potential, and then we have some atomizing gas, and basically an arc is produced between those two electrodes. So, we have positive potential, negative potential. It can be one kind of wire, it can be different kind of wire, and they can be even same kind of wire. So, and in turn basically it is producing nothing but arcing will produce the droplet of particles that now impacts on a particle substrate to deposit them as a coating. So, this is arc spraying, and in this process, as we can see, since we utilize two electrodes, we can also produce bimetallic coatings or even different kind of materials. We can also have a cored wire. So, we can do alloying in the core of the wire and still we can produce an arc. So, we can control the overall composition of the material as we please. The third part is high velocity oxy-fuel. In this case, we have a gas feed, and then we have a powder inlet for letting the powder come. But the overall we see here is that we accelerate in case the fuel is the fuel, we have certain fuel and this oxidizer, this oxygen, and then basically fuel and oxygen they combine together and they are accelerated to a specially designed nozzle that creates the supersonic speeds of this carrier gases, and in process we get very high velocities to the order of 3 to 4 Mach, and that takes the powder particles, and mostly because of the plastic deformation we get the coating on the substrate. It is not much because of heat. heat is approximately similar to that of a combustion process. So, the temperatures are approximately 3000 degrees centigrades or so, but it is mainly because of the high impact or the high momentum which is basically being carried over by the molten particles that result the final coating. So, we see the substrate and we get the coating which is very fine, it has a minimal porosity because of the high deformations which is occurring in the material. Then we have something called plasma spraying. In this case, we have a tungsten cathode and a copper anode which is surrounding it, and then a arc is created between tungsten and between the cathode and the anode, copper anode and tungsten cathode. And then one more thing in HUF is we have to supply the powder somewhere. So, in case we require the powder to be fed and some location, and then the overall flame which is being generated. So, depending on the residence time of this particular particle, it will get molted and it will acquire certain heat content. Same thing happens in plasma spraying, that we can either once we generate a plasma because of the arcing between the copper anode which is surrounding it and the tungsten cathode, we generate certain arcing, and that creates the plasma, some plasma plume. So, either we can insert the powder particles right at where the plasma is forming or little farther from where plasma is forming. So, if it's being fed within the gun, it is called internal feeding. If it is being generated outside, it is called external feeding. So, we can either feed the material outside, that is called external feeding, or it can be generated, the powder can be fed inside the gun, that is called internal feeding. That is very essential because it is very essential for high melting materials, because the high melting materials such as ceramics, they require prolonged stay in the plasma plume. So, if we are adding them as soon as the plasma is, as soon as where plasma is forming, then it will stay in the plasma plume for a elongated time. So, certain ceramics such as aluminum oxide, yttriacyl zirconia, certain ceramics, they need to be fed right where the plasma is forming. But for external feeding, it is basically essential for low melting materials such as magnesium, aluminum and so on, because if we start feeding the material right where plasma is forming, it has enough time to get melted and splash. Once it splashes, it can even choke the nozzle, the nozzle of the gun. So, they need to be fed outside. So, still they have enough temperature available to get melted, then accelerated by the carrier and to be taken up by the carrier to get deposited on a substrate. So, we see a substrate. So, we require a certain standoff between the gun and the substrate material, so that the particles, they acquire certain velocity, they acquire certain heat, and then they get deposited onto the substrate. So, there are certain property dependence, like coating property dependence. First thing is plasma or flame jet formation. That basically depends on how we are generating the heat, either it is by a flame or it is by plasma. So, there are certain concerns how the torch is being designed. So, once we are forming the plasma, whether it is very constricted, so we can get a constricted flame, or is it expanding, or it is again constructing like a like an arc So, the overall things depends on the overall flame or plasma jet formation. It also depends on how much power we are supplying it, or how much is the capability of the gun to withstand certain heat. So, the overall dissipated power and even how it controls the overall mass flow rate. So, if you want to control very high deposition rates, we need to provide very high capability of the gun to play with high mass flow rates. So, the overall flame and plasma jet formation is being dictated by certain things. Again, the powder and its injection is also very critical, because first thing is chemical composition, what sort of chemical composition we want to play with. Also, there are certain sizes and distribution of particles. If you make the powder particle very big, then there may not be enough heat, because heat will get absorbed by the bulk of the material. So, there will not be any heat left to melt the surface and then make it plastically deform. That may not be possible. If we keep the powder particle very small, then because of upon its impact with the substrate, it experiences a bow shock. So, the overall momentum of particle may not be enough to overcome the bow shock, and it will just get scattered. So, it will not lead to any deposition. So, once powder particle is very huge, it is not molten enough, it will just impact the substrate and it will bounce off. If powder particle size is very fine, it will again, it will not be able to overcome the Bow shock and it will again just fall off. So, that is the disadvantage with the powder size and distribution. So, we need a certain size generally which is between 15 to 45 micrometer in diameter. Again, depending on that, we also need to say whether we want to have internal feeding. So, overall shape, length, position of that particular injector, and also for the trajectory which is being acquired by the powder particles to finally deposit a coating. Second, third at most importance is the enveloping atmosphere. So, if we have an air, then we have chances of oxidation. So, sometimes we need to maintain either inert gas or we have to maintain low or high pressure. So, that depends whether we want to create a vacuum, but then again it makes the process very costly because we have to do the entire spraying in a vacuum chamber. So, these are certain constraints to it. Again, substrate cleanliness, its roughness, even oxidation state, preheating, even the thermal characteristics of the substrate are very important in terms of dictating the properties of the coating material. So, relative motion of the torch and substrate is also very critical, because if we are trying to go very slowly, we are basically building up the heat in the material. So, in the process we are not really if we are moving very high very slowly, then we are just building up heat in the material and much higher deposition rates can be achieved, but that might result the overall development of thermal gradients and that can result into cracking. And if we go very slowly, we are depositing very less material, and in that process also we are not allowing the much heat development into the material, and then it might just cool off, or it may not, the heat may not be sufficient for the material to get deposited on the material. So, in both the cases we need to somehow maintain or optimize the overall feed rate or the overall motion of the torch and the substrate, so that coatings can be formed very nicely. So, the overall schematic diagram of thermal spray metallic coating, we can see that in case of thermal spray coating, we achieve a sort of structure. So, if we have a substrate is generally very rough. So, we need to deliberately keep the surface very rough, and in process, once a powder particle comes, it impacts the surface, it basically flattens up, it flattens in a very rough manner. So, we can see the development of certain splats. In between, what we can get, we can also get some unmolten particles, because these particles are not heated to a large extent, they get molted, they don't get melted, they just remain as it is. So, it is unmolten particle. Once it has acquired enough heat, it can also undergo certain oxidation. So, we can see, we can also achieve some particles which are unmolted and unmelted, or some which are basically being oxidized. That is again a problem. Inherently, since it is forming splats, there is some sort of a interlamellar porosity which is available. So, we have something called interlamellar porosity. At the same time, since surface is very rough, it might happen that some of the pores they remain as it is. So, we can also achieve some sort of a porosity in the coating. So, inherently what we are seeing, we have unmelted particles, some oxidized particles, interlamellar porosity, or even certain micro porosity which is available, which are nothing but voids, and again the surface roughness is essential. So, we can see the overall defects which can be basically being creeped in the thermal spray coatings. Again, with certain chemical interactions such as surface oxidation will lead to oxide inclusions. That is what we are seeing here, that we can get some oxidation of the material, such as in reactive materials such as titanium. It can also absorb other gases such as hydrogen and nitrogen, it can form nitrides and hydrides. But typical microstructure of this plasma sprayed or thermal sprayed coatings appears more like this, that it is a very splat kind of a structure. So, they will show lamellae kind of a structure. So, we are seeing these are nothing but splats which are growing basically one over the other. So, we can see much deformed structure which is more like this. So, this is the overall structure of a plasma sprayed or thermally sprayed coatings. We can see stringers or lamelles which are basically nothing but spreaded splats. So, this is nothing but a typical microstructure of a metallic thermally sprayed coating. So, it is undergoing both, it is undergoing heating and then basically it spreads out to form a layer over the already existing surface. So, and that deposition is occurring because of the interlocking of this particular splat with the existing surface. And as we said earlier that the cooling rates are very high, 10 power 6 to 10 power 8 kelvins per second. So, it is also very useful in terms of creating certain amorphous phases, such as glassy metals or glassy ceramics can also be produced, because glassy materials they can be highly degradable. So, if we can make those glassy coatings on a biomaterial or a device material, that can basically get dissolved into the body because of their high dissolution rates. So, we can also basically form metastable or amorphous coatings on a particular implant surface. Further, we can see the splat microstructure. So, as soon as we have a splat, first of all we have molten particles, it impacts on a substrate and then it basically forms a splat. So, we have center portion which basically now goes on to forming a splat. So, we can see initially the particle, the molten particle was spherical, and upon impacting with the substrate it forms a certain rim around it. So, we can see a thicker rim which basically forms, and if you take its cross section it appears more like this. So, we can see that overall thing. So, we can see it has certain thickness, and this thickness is much higher in the central region, because here was the overall center of gravity for this particular splat, and then the fluid starts flowing towards outside and then it forms a certain rim. So, rim is again it is little thicker. So, that's what is happening, that material starts flowing on the outside, and because of the resistance from the air, or as soon as it starts solidifying, it develops certain mass again little bit here. So, this portion is little thicker than the little inside portion out here. So, that is what we can see the schematic diagram of thermally sprayed spherical particle. So, initially we had a molten particle which was spherical, and then it forms a splat. So, these splats deposit over one another to form or develop the final deposit, and this characteristic of this particular splat is dictated by the melting point. If melting point is very low, there will be much more fluidity available for the splat to basically spread. Degree of superheat, if we superheat the material, again we have very high energy or high fluidity available for the splat to spread itself. Viscosity, if viscosity is very high, it will experience certain friction from the substrate as well as from the surrounding, then it will basically try to constrict as a molten particle itself. It may not try to spread to that extent. Again, its interaction with the substrate, if the interfacial energy or the thermal gradients are supportive, then it can basically the overall spreading can be dictated by the overall interaction with the substrate. So, if substrate and the molten particle they have lower thermal lower interfacial energy, it will try to spread. Again, if the substrate has very high thermal conductivity, it will absorb the heat as soon as possible, and again the particle will not get time to spread. So, again there are certain aspects to the interaction of the molten particle with the substrate. There is one more nice contrast between what happens in air, surrounding air environment, and what happens in vacuum. So, this particular powder particle, if it tries to impact on a substrate, it will develop a splat of certain size with certain stringers like this. So, it will have certain dendritic arms around it, but it will not spread to that extent because it is experiencing certain resistance from air. So, we have a molten particle, it impacts on a substrate and the atmosphere is air, but it will not basically flow to that extent because of its resistance with the air. But in vacuum, what is happening? It is not experiencing any resistance. At the same time, it is also achieving enhanced thermal superheat. So, what happens in this case? It will try to spread out to a very large extent. So, if we had a splat, upon impact it basically spreads to very thin. So, it is very thin. The overall diameter is much more than the diameter of air. So, diameter in vacuum is much higher than diameter in air. So, that part we can observe from here because it is experiencing very low resistance from the surrounding or the environment, and also it is experiencing much higher heat. So, the temperatures are much higher here. So, temperature in vacuum can be much higher than temperatures in air. So, overall we can see that a splat microstructure is very different once it is being deposited in air or deposited in vacuum. And generally we see the overall microstructure, it develops more like this. Just to take you a high resolution. So, we have a splat we have second layer of splat, third layer of splat, and in process we see it forms some sort of a columnar grain structure. So, columnar because heat is being extracted in this direction. As soon as this is impacting the substrate. So, this is a substrate, the heat is being dissipated in this direction. So, we see the overall growth is also occurring in that particular direction where heat is being extracted. So, we can see formation of certain columns like this, and similarly the other layers also start forming a columnar structure which are more like that. So, generally we can see we have a lamellar structure, these are nothing but lamellae, and then we have a columnar grain structure which basically forms in the thermally sprayed processes. At the same time, what we can see here is that it also depends on the location or how the surface is. So, if you have polished surface, then we have a deposited splat, one more splat, then we see the columnar grain like this. This is a smooth surface. If we start taking a grit blasted surface, then what can happen? The surface will be much more rougher. So, we will see one splat will basically be form like this, second splat might form like this, and it will have eventual columnar structure, because it depends on where the heat is being extracted. So, we have a grit blasted surface, and consequent splats, they will start coming onto the existing surface. So, if this is the existing surface, I will get the next splat probably like this, third splat probably like this, next splat probably like this, and in this case also, now I will get splat like this. Again, this surface now become rougher, though it was initially polished, now it is becoming much more rougher, and I will get consequent development of splats like that. So, it depends on the roughness or smoothness of the surface. And as we can see, the rough surface is providing much good interlocking. So, now it can provide much good interlocking along the interfaces. So, the rougher the surface, the better interlocking it can provide to the deposited coating. So, that is the advantage of this particular that is the advantage of the surface roughness in case of development of a microstructure in thermally sprayed coatings. So, one more thing which is inherent to the splattening is the overall flattening degree, because the flattening will decide how much area will be covered to an extent. So, if you have a very rough surface, so there are more chances that certain porosity or voids can be retained. So, we want to provide much higher degree of flattening or higher degree of filling in those particular pores. So, we need to achieve a very good flattening, and that flattening is dictated by this particular equation. The flattening is related to a particular constant, Reynolds number, to a certain again constant. So, we can see that flattening is basically depends on the Reynolds number. Again, it is given by V d rho by mu. So, V is the velocity, d is nothing but the overall diameter, and rho is nothing but the specific mass, mu is nothing but viscosity. So, we can see the V d rho by mu, the Reynolds number, and again K and A are again the constant, which basically are fitting parameters. So, for a good splat model, we need to basically take account of the overall particle flattening. Again, what is the sort of solidification start at the hypercooling temperature, how the nucleation is also occurring. So, nucleation phenomena also has to be correlated with the overall flattening, because as soon as it starts flattening, it also is solidifying. And again, we can see the evolution of contact at the flattening point and the substrate is also very critical. There are certain other concerns as well, like the solidification and heat transfer also dictate the overall development of the coating. So, the mode of heat transfer for splat, that dictates the overall rapid conduction, because as soon as a splat is being deposited, it is experiencing some sort of a conduction, it has to conduct the heat for its solidification. So, it correlates well to the feature of the rapid solidification, and that in turn forms the secondary dendrite arm spacing, or that also dictates the overall splat thickness. And again, the direct cooling rate measurements, they are very inaccurate, because you need to put something inside the particular splat to basically determine its temperature, and that may not be really feasible. And so, there is an imperfect contact between the melt and the thermocouple. So, even if you put a particular thermocouple on the substrate and let the splat deposit onto it, still there will not be any sufficient contact. So, that will again lead to certain inaccuracies in determining the overall temperature. Then again there can be certain material overlapping. So, if in case one splat is being deposited, in process second splat might come and just impact here. So, again we are not able to judge the overall temperature which is being generated because of this particular splat, or the degree of cooling or solidification that is occurring incurred by this particular splat. That may not be really accurate. But still, even if you can measure somehow what is the overall cooling rate by putting the thermocouple on the substrate itself, still that particular information will also be very useful. So, that is what is the overall attributes of thermal spraying, that we need to see what is the overall solidification and the heat transfer that is occurring in the splat to result the final microstructure. The cooling rates basically can be provided by seeing in turn the overall dendrite arm spacing. So, we can see the overall dendrite arm spacing depends on the average cooling rate, and that is a inverse proportionality. So, if you have very high cooling rates, the overall dendritic arm spacing or the generated microstructure will be very fine. So, we can see the overall dendritic arm spacing or the features of this particular microstructure is inversely proportional to the overall cooling rate, where A and N are the material dependent constants. So, depending on that it will have a effect. Again, splat thickness, again it is basically being correlated that the splat thickness is basically dependent on the overall solidification time. So, higher the solidification time, basically it basically will result at certain dependence on the overall splat thickness. Again, cooling rate is also given by its dependence on the splat thickness. If splat is becoming very thin, we can achieve very high cooling rate. So, that is again because if I have a very thinner splat in comparison to a thicker splat, I will need more time to excavate the heat or take the heat out, whereas in this case my cooling will be very rapid. So, as I see, if I have a very thin splat, I will achieve very high cooling rates, but in this case my cooling rates will be much inferior to that of the second case. So, the overall solidification rate for this sort of Newtonian cooling is basically given by the difference in the substrate temperature and the melting temperature of the splat. So, we have melting temperature of the splat minus the substrate temperature, and with certain dependence of the heat transfer coefficient, the overall density of the splat, the specific heat and specific heat capacity of the splat and the splat thickness. So, we can see the overall solidification rate, how it is dependent on the properties or material properties and the temperature which is being available. So, we can see that melting temperature and the splat temperature and the overall coefficient of heat transfer is basically being given by H, and then we can see the thermal gradient finally which comes out to be is the difference between the melting and the substrate temperature divided by the splat thickness. So, we get certain component in terms of Kelvins per meter, that is the thermal gradient, and the solidification rate is being given above. So, for certain regimes we can see the overall interplay of solidification rate and thermal gradients, it will result to generation of certain microstructural features, and that will dictate the overall performance of a particular material. So, depending on whether we are getting cellular microstructure or a planar growth is occurring or a dendritic kind of growth is occurring, that is being dictated by the thermal gradient as well as the interfacial velocity. So, we can see if I have a, so I can see overall that if I have an interfacial velocity, certain term r, it will be in meters per second, and then I have a thermal gradient that will be in Kelvins per meter. So, we can see I can get if I can cool my material very rapid while achieving a very slow interfacial cooling, slow interfacial velocity, I will get something which is called a planar growth. And in other case, if I am able to get very high interfacial velocities, whereas I keep my thermal gradient very minimal, what I get is some sort of a dendritic structure. But if I keep my interfacial velocity in par with the thermal gradient, what I get is some sort of a very refined microstructure which is called a cellular structure. So, what I am getting is, if I keep my thermal gradient very high while minimizing my interfacial velocity, so the solidification is not occurring at that particular higher rate, but whereas I have very high thermal gradient available. So, what I am getting the entire material is getting transformed or solidified. So, I am getting much coarser or planar growth of the material. If I am keeping my interfacial velocity very high while not providing it enough thermal energy, the gradient not enough thermal gradient, then what I get is nothing but a dendritic structure. So, I achieve some sort of a dendritic structure with secondary arms, primary arms and so on. In this case, I am getting very coarser microstructure because I am getting a very planar growth. So, the entire interface basically starts growing in a similar fashion, but in this case I get very refined microstructure. So, that is the advantage of the interplay between the thermal gradient and the interfacial velocity. So, by controlling them I can achieve a very refined microstructure. So, that is the overall play with the thermally sprayed coatings. So, depending on the kind of gradients I provide, whether it is interfacial velocity or the thermal gradient, I can interplay with the overall material properties to provide the thinness of the splat to let it achieve very high solidification rate. I can supply very high thermal gradients to it by enhancing the cooling rate and so on. So, I can somehow control the overall structure by utilizing various material parameters as well as the spraying parameters. Again, the problem, if we can model it very nicely, that will be very good, but the overall problem is the entire process is occurring in tens of microseconds. So, splat, it gets heated up, molten, accelerates and impacts on a substrate within tens of microseconds. So, the process is very rapid, and basically the layer is formed in couple of milliseconds, and again it is only few seconds by the next pass basically will come. So, the overall process is very dynamic, and the particle size we are talking about is a micron size particle. So, the overall it makes the process very complicated. So, the model will have to deal with certain simplifications, such as we can deal only with the splat, or we can only deal with the piling of the splats to form a layer, because we are seeing two scales. One is the splat level, second thing is the overall again the microstructural part. So, we have certain lamellae, then it is forming some columnar structure, and again there is a deposition of all those splats. So, we are talking 2 or 3 orders of hierarchy in this particular structure. So, it also includes certain roughnesses. We can also have melting, we can also have unmelted particles, we can have temperature with splat, temperature is also a variable, particle size is a variable, temperature and shape, direction, composition. So, we can see there are so many variables which are inherent in the modeling of a splat to result a coating. So, that makes the process very complicated and very dynamic, and that creates difficulty in effectively modeling it. Again, the reproducibility and reliability of the coatings also an essential components in terms of designing the biomaterials, because if you want to create a coating, it needs to be what we are intending it to be. So, but again there are all these factors such as the controlling rate, the microstructure, even the parameters of the gun. So, we have to play a lot with them to in order to understand it, to be able to model it, and to understand it better we need to basically create some sort of process map to see where we can fit in our coating requirements and where we can choose the parameters from. So, there are many errors associated, which can be design errors, some operator errors. There can be also process instability, that is being inherent with the process. So, there is a fluctuation in the voltage, or there is fluctuation in the movement of the gun. There can be handling errors. So, even when we are utilizing a particular material, if we shake it a little bit, the heavier material will settle down, whereas the lighter material will basically float up. So, in deposition, first the heavier material will just get deposited. So, second time if we do the same coating in the same parameters, we might get some very different result. Again, there can be post treatments, those errors can also can creep in. Also, the kind of surface preparation. So, we have to get a better control of the surface preparation. Sensors also should be very robust, and again we have to have the theory, but it should be backed by the experimental results or the measurements to back the theory, and somehow establish certain empirical correlations. They may not be exact in nature, but they have to be empirical in nature. So, not backed by not exactly being that what is being predicted by the theory, but what we are actually seeing, and then we require a nice understanding at all the levels, starting from the splat formation of splat, its thinning down, the generation of microstructure, and the layering of this particular splats to result in overall deposition, to finally achieve a standardized procedure of depositing the coating and achieving the controlled structure as well as thickness of those particular coatings with certain specified requirements. So, that is what is required in terms of getting a particular coating with a nice reliability and reproducibility. And recently a new term has come into picture, which is called nanostructured coating. It has come to an eye because it has a potential for significant improvement. It can basically nanostructure is nothing but reducing the overall microstructural features by 100 to 1000 times. So, generally we have structure in terms of structure which is thicker enough in terms of micrometer range. If you can make them into nanometer range, it means we are getting nanostructured coatings. It has myriad advantages, such as it can have higher hardness and strength. The reduced grain size basically reduces the slip distance. So, in eventuality we can also reduce the defect size, and that can provide much toughness in ceramics. So, if you are making hydroxyapatite coating on a particular surface, and if you can retain the size or the microstructural features in the size range of a couple of nanometers, we can achieve much enhanced toughness, and that is the criticality of any ceramic component, that we want to get maximum toughness out of it. So, if you are able to achieve a very fine grain size, we can enhance its toughness. Again, if we can make the material much more amorphous, such as in glasses, that is again a boon in case if we want to make that particular glass dissolve with time. So, for biodegradable components, we can again utilize this particular process. So, instead of making nano, we can also make amorphous coatings. And since we have enhanced grain boundary, it leads to stress relaxation, because now these fine grains can align themselves, they can orient themselves, they can rotate themselves to result a stress relaxation. At the same time, they also increase in diffusivity. So, that also is good, because it will result in a uniform microstructure, uniform composition throughout, and also it might also result in a reduction in the thermal conductivity, because we have now very high defect regions. So, there is much more of grain boundary area. So, much more vacant area, which is nothing but an insulator. So, we can achieve much reduced thermal conductivity by refining the grains. So, if you want to provide a thermal protection, we can also go for this nanostructured coating. And also, since the grains are very fine, we can also achieve very uniform corrosion properties. So, instead of observing a pitting, such as which is being observed in say steel, we can avoid this particular feature once we utilize a nanostructured coating. So, we can see nanostructured coating, they have potential for significant improvements. They can provide much higher hardness and strength by reducing the grain size and slip distance. They can provide much enhanced toughness in ceramics, and they can also lead to stress relaxation. They can increase the diffusivity. Also, they can reduce the thermal conductivity. So, those are the certain advantages of nanostructured coatings, mainly because of their enhanced toughness in ceramics. These are being targeted for. So, in summary, we can see that the thermal spray coatings, they have emerged as a tool for coating a bioimplant material or a device material to provide certain functionality to it. That is basically the interaction of this implant or the device material with the surrounding tissues. So, it can provide a compatibility. It can be either arrangement of certain pores or certain chemical composition to provide it friendliness with the surrounding material or surrounding environment. But again, modeling with improved definitions are required, and it is required that we establish certain empirical formulations for certain spraying conditions and come up with a process map to select certain property with certain functionality or the microstructure, and be able to find a reliable correlation between coating properties and the particle parameters or the processing parameters. So, we can finally achieve some standardization and reproducibility. So, that is highly required for achieving a good and reproducible coating again and again. And recently nanostructured coatings have emerged, which can provide much enhanced toughness and enhanced mechanical properties to a surface coating. And again we can see by controlling the thermal gradient and the interfacial velocity, we can somehow control the microstructure, and in process we can also control the we can evolve with some empirical correlations of the processing itself, and now we can join these two in order to achieve the maximum benefiting properties for a biomaterial coating. With this, I end my lecture. Thank you.